So this is actually a step 3 question. However, the sort of topic it's asking about is complex numbers, and it's been moved into step 2 in recent years. So this is question 4 from the step 2 complex numbers sport booklet. So you expect to see this kind of thing in step 2 now. Anyway, it's question 8 from 2005, and let's just get into it. So z is a complex number, so it's just like x plus iy. Z star is therefore x minus iy. And of course, the modulus of z, because we're thinking about moduluses here, is the root of x squared plus z squared. Now, there's a bunch of results in here about complex numbers and their conjugates, which I'm just going to call stars, that you should probably just go into the exam knowing. I'm going to prove a lot of them here, but just go into the exam knowing them. Here's the first one. Of course, z times z star is going to be this times this. If you expand it out and then cancel out these terms and make that a minus to make the whole thing a plus, you end up, of course, with actually, if you just square both sides here, mod of z squared. Go into your exam knowing this result because you do not want to have to waste time trying to derive that in the middle of everything else. So just go into the exam knowing that. What we can do then is we can now say, well, let's consider a minus c, where a and c are both complex numbers. So maybe a is like a, we can of course firstly write this as this based on this result here. Sorry, no, we can't, based on the fact that I've just sort of let it equal to this. Now, if a was a1 plus a ia2 and c was c1 plus ic2, now omega star is just going to be what happens when you make the complex bit negative. Now, since the complex bit is currently split up, we can group it together in the same place, then make it negative, then ungroup it, and just notice that this means a has become, which was this, has become a star, and c has become c star. So omega star is a star minus c star. Again, just if you just know that if you've got a complex number that's made up of other complex numbers and you star it, you just star the other ones separately like this. Just again, just go into the exam knowing that. And of course, when you expand that out, you will immediately end up with the thing that you were trying to get you to get to, which is a minus c modded or squared is equal to this business there, and you're done. So that result is now done. Hence, prove that the triangle AOC in the diagram, whose vertices are represented by O, 0, A, and C, is right-angled if and only if this. Now, right-angled if and only if makes me think immediately of Pythagoras, because Pythagoras holds if and only if there's a right angle. So I'm doing Pythagoras here at some point, almost certainly. Also, the fact that there's a square here lends even more, and a modulus lends even more credence to that. So, okay, we've got a point A, which is big A is just the vertice A, or the vertice big A is just the complex number A, I should say. So that's there. And then C is maybe here. Mod A is, of course, this length. Mod C is this length. So this length here, well, that's the vector C minus A or A minus C, depending on which way you go. It's not going to matter, of course, because the length of that is the same either way. So we're going to say this. And of course, if this is right-angled, Pythagoras will hold. So if right-angled, mod of c squared equals mod of this squared plus mod of that squared. But of course, we just saw that this thing here is c star. And this thing here is a star. And this thing here is the thing that we just showed up there. So we can put that result in, we can put these two terms together and cancel out some other stuff, and then move it over, and we end up with this. And that will be the next part done as well. Good. Now, always write down the things that you've previously learnt in your step question. Never forget things. Those are the two things that we've done so far that might be helpful at some point. P and P dashed in the diagram are represented by these 2 points made up of A's and B's, I guess, where B is just a new complex number that they've got in now that's non-zero. A circle has center C. Remember, C was just the complex number C. And point A, again, just complex number A, which is on the circle, because the circle centers C and goes through A. But also, A is a tangent to the circle. Well, of course it is, because previously we just saw that these are right-angled, if and only if this. And now we're saying it's a tangent, but tangents meet radiuses at right angles. So this is definitely going to hold for this question, because this says this is true if and only if right-angled. We know it's right-angled because tangents meet right angles meet radiuses at tangents. So perfect. That's all good. So we can use this result at some point, which is excellent. This result is just true. So we can use this result as well. Now, if we consider some other random complex number on the circle Z, this distance, of course, is Z minus C modded, or C minus Z. It doesn't matter which you wrote. But the whole idea, or the whole point of a circle, is that this has got to be equal to this. The lengths have got to be equal. So we can say this. We could square both sides, and the point of squaring both sides is to use this result for both. So let's throw in that result for both. Of course, if you put in Z, A and Z are just complex numbers, so you can just replace all those with Z's instead. So we get to here, some stuff cancels, which is useful, and we get down to here. But the thing is, this thing is right-angled, right? It's right-angled. So therefore, this result holds, and if you look in there very sneakily, this is minus this plus this, which is 2AA star. So that result holds because of Pythagoras, because it's right-angled. So we get down to here, and we can clean that up a little bit, and we get to there. Now, why have I done any of that? Well, because now, I've just said Z represents any point on the circle. So now let's just test this result here for this and this, the 2 points that they're actually asking me to look at. So let's put point P in here in place of Z. So it becomes this. Now, P star, again, probably a result you just want to go into the exam knowing. Well, P is just AB, it says, and P star, sorry, is AB all starred. Now, the result is this is just A star, B star. But if you just want to very quickly prove it, here's a very quick rundown of the proof. I'm not even going to talk about it. I'm just going to let it happen. There's the proof. So AB all starred is AB starred. So if you're timesing two complex numbers together and then taking the star, you're just taking the star like this. Again, a result that you just want to go into the exam knowing to save yourself a lot of time. Same thing here. Now we're going to do some more work with that. Well, we're going to leave that there, sorry, and now move on to P dashed. P dashed is when we put this result in. And again, P dashed starred, I'll leave the proof to you, but it's just A star over B. I'll leave that proof to you. And we get to here, if we times everything by B star B, it will look a bit more like this, I think is what I did there. And yeah, we have this result and we have this result. And if you look at them very carefully, you'll see that this matches. Or does it match? Where does it quite match? This one is, yeah. I've written the terms. I've been stupid and not written them in alphabetical order, which makes it harder to spot. You should just write things in alphabetical order when you're doing maths. But this is the same thing. So basically, we're saying if P is on the circle, it must satisfy that. If P dashed is, it must satisfy that. These are the same equations. So therefore, if one of them is on the circle, the other one definitely is as well. For sure. Conversely, show that if the points are on the circle, so if the same 2 points here we just investigated, if they are on the circle, show that we now have A being tangent. In other words, show that A does make this right angle that we took for granted earlier. So we're doing the opposite version of the question. And really importantly, what that means is we can't use this result anymore, which we used halfway through the last question, because this result holds if and only if there is a right angle. But we don't know there's a right angle. We're being asked to show that. So if we could show this, now this is just a technical point, if we could show this equation is true, then great, we've shown there's a right angle, because this equation only comes if and only if there is a right angle. But we have to show this equation to show there's a right angle, which is what I'm being asked to do. So, okay, that's what we're being asked to do. Doing it backwards, and we're not allowed to use this result just yet. So, okay, now, if P and P dashed are on the circle, they must satisfy this equation that we talked about before, because the radius is the same all the way around a circle. So we can put these things in. I mean, firstly, I'm using this result, this is the very first thing we did. It's always true. So I can put that result in just like I did in the last question. And now we can put in these 2 points and say both of them have to satisfy the Z bit. The A and the C are just referring to the A and the C, which we know. Sorry, it's important to say we know A is on the circle because the circle passes through A. We're just trying to prove it makes a right angle. So we know A is on the circle still, so that's why this still works. But anyway, we're going to put in our 2 results for P and P dashed into the Z bits, which will make this, which expands out to this. Again, I'm not proving the results this time. I'm just going to take them for granted. And then we're going to put in A over P dashed in as well. And again, just, I think, timesing everything on B dashed again, and we get this. And this green one and this purple one are the 2 equations that we can use. So just this one and this one. And again, the aim is to try and show this. I've rewritten it a little bit from here. I've just put this on the other side. But if I can show this, then if that's true, if and only if there's a right angle, so this shows that there's a right angle, if I can show this is true. So how can I use these 2 equations to show this is true? Now, this is not too easy, but what you can maybe notice is that the left-hand side of the top equation is basically the same as what I want here, except there's just one less copy of AA star. So let's just add AA star to both sides of this equation here to get this. And now what we can see, if you spot it very carefully, and again, writing terms in alphabetical order would help a lot, but now we can spot, having added AA star to this equation here to get these 4 terms, these purple terms exactly match. If you just look at them, they do exactly match, which means that I can just throw in this side of this equation, the second one, into here. So now I've used both equations, which is excellent. And now this term has a BB star in it. So I can factorize out BB star from all 4 terms to get this. And now if you add these 2 things together, you see you get an exact second copy of this business here. Now I glossed over this in the question, But apparently BB star is not equal to 1. So therefore, this can't just be this times 1 is itself, because this isn't 1. And the only other solution to this equation is that this whole thing must be 0, because you can't times it by anything other than 1 to get itself. So therefore, this whole thing must be 0, and we're done with the question. Really nice little question. Thanks for watching, and I'll see you next time.